All right, so it's 10 o'clock. It's time to get started. So my talk is low-level shade optimization for next-gen and DX11. And if you were on last year's GDC, maybe you were at my talk there, the low-level thinking and high-level shading languages. And this talk is going to be kind of similar in style. It's going to be a similar kind of optimization we're going to talk about. But it's going to be more like focused on the next generation of consoles and DX11, and in particular the GCN architecture. So last year I covered basically the basic feature set. We're talking about basic DX9 level of operations, mostly floating point. Of course, a lot of things has happened since last year. We have new consoles based on GCN architecture, and DX11 is very mainstream now. A very large portion of the users on Steam have DX11 level of hardware. So it of course makes sense to make a new talk where we talk about things that are specific to the GCN architecture and in general about DX11 level hardware. So the main lessons from last year is that you get basically the code that you write. You can't really rely on the compiler optimizing too much for you. And this is basically because there are semantics in the language that you can't really change without risking that operations fail or don't get the result that you expect, even though these are sort of corner cases in the IEEE standard for a floating point. And the other lesson from last year is that you should write code in the multiply and add form, because all hardware since the beginning of time has been made for multiplies and adds. A multiply followed by an add can be done in a single cycle, versus doing things in the other order, doing an add followed by a multiply is two separate instructions. So it's always faster to try to match this form of operations. Another lesson is that you should separate scalar and vector work, because all hardware is more or less based on scalar, or some are VLIV architecture also benefit from this. Actually, even vector architectures usually benefit a little bit by separating the scalar and vector work, because you can parallelize things, put things into different lanes, even on that hardware. So this is actually one of the optimizations that can give you the most bang for the buck. It's very easy. Usually just add a parenthesis and stuff, and suddenly your code is a lot faster. And you can even look inside the built-in functions to find opportunities to do this sort of optimizations. Other lessons is that if you do absolute value or negation of values, these should be on the input operations, where saturation should be on the output. These are just modifier on instructions, so these are for free if they happen in the right place. And if they don't, they will cause another mob instruction to be inserted. So things like square roots, reverse square root, exponentials, trigonometry, these are mapped to hardware instructions, so they are fine to use. They're a bit slower than regular operations like adds and multiplies, but they aren't horrible. For the exponentials and logarithm, it's the power of 2 functions that are native. It's not the natural logarithms or the E-based ones. They generate another instruction just for changing the base. The thing you should watch out for is inverse trigonometry, because these things doesn't match at all, doesn't map to any hardware instructions. So they are emulated with dozens or 20 instructions to evaluate those, so they can be really expensive. And finally, of course, even if this talk is focused on low-level optimizations, it doesn't mean that high-level optimizations is something you should be doing. You should really be doing both if you try to have a sort of technical leadership. So let's look a little bit about what happened to modern hardware in the last 7 or 8 years since the last generation of consoles. Obviously, a lot of things have changed, so all the assumptions don't really hold true anymore. So if you just look at this very simple shader here, it's just taking a texture coordinate as input, sampling a cube map, and returning the results. And for the reference, the D3, the bytecode, is on the side there. So at least as far as direct read the bytecode is concerned, it's still a single instruction. So by the range of hands, how many think this is still a single instruction on the hardware? Nobody? Okay, good. So who thinks like maybe 5 instructions? Or 10? 20? Who's with me? 50? Okay, nobody raises hand on anything. Anyway, so this is about 20 instructions. This is the shader on the hardware side. So in the past, actually, it has been like a single instruction if you're talking about like DX9 level hardware. But nowadays, obviously, a lot of things have changed. A lot of things have moved to the ALUs. So in this example here, we have 15 vector ALU instructions, of which one is a transcendental. I will talk more about this. The transcendentals are a bit more expensive. There are 6 scalar ALUs. I'm going to talk more about the difference between vector and scalar ALU operations later. There's one image operation, the one in pink there, which is basically the instruction that will sample the texture in the end. And there's one exporter in the end. So this is the operations that you have in the shader here. So a lot of things have happened on the hardware. So the general trend is that fixed function hardware is moving into the shader cores, into the ALUs. Things like interpolators, these used to be free. In a sense, it at least came preloaded into registers when you started the shader. You didn't pay any cost in that way. But nowadays, it's handled by the ALUs. Vertex fetch has been there hasn't really been a fixed function hardware for that in a very long time, actually. Even the Xbox 360 had that as baked into the vertex shader. So things like vertex declarations and things like that isn't a hardware object in any sense. Export conversion is something that happened with the GCN architecture. Now, in the end of the shader, you need to actually convert the format for the export. Projection and cube map math, like normalizing the coordinates. As we saw in the example there for cube map, these things are handled by the ALU these days. And gradients is something that's been kind of walking back and forth a little bit. It used to be an ALU instruction, then became a texture instruction, now it's back to ALU again. But nowadays it's actually not implemented as a separate instruction. It's a sort of general swizzle between the lanes and then followed by subtraction in the shader to find the gradients. So a lot of things that used to be sort of handled by fixed function hardware has moved into the ALUs. And this, of course, makes a lot of sense because you want to make the most out of those shader cores that you have that already is capable of doing a lot of math at very high frequency. And the other thing that's happening is that most of everything is backed by memory these days. So there's no such thing as constant registers anymore. And textures and sample state and buffers, all these, the descriptions of these aren't in sort of some kind of device registers anymore. They are just a piece of memory that the shader loads, and then it knows where your texture are and what sizes and resolution they are and so on. And this, of course, means that you also have basically unlimited resources. You don't have any sort of fixed slots that you can just squeeze in, say, 16 sample states. That's not a hardware limitation. That's pure an API limitation. And you can load as many sample states of textures as you want from a shader. And the compute units, they are stateless these days. So that means that once a compute unit starts working on a shader, it has all information within its own little box. So it's not in any way dependent on any big device state. It has everything in its own registers. And that means also that it can run asynchronously with the graphics pipeline, for instance. Or between different compute units can run different shaders. So if you look back a bit on say, DX10 level hardware, one kind of fun exercise they can do is try to write a shader that actually outputs no instructions at all, or at least only an export instruction. So this is how you might have done it on DX10. You just take the screen, or take an interpolator he has to return it because interpolators came in a register and the output was in a register there. So there's no ALU instructions to execute this shader. But if you bring this onto DX11 level hardware, it's not so null anymore. As you can see, already on previous pre-GCN DX11 cards, you already had interpolations handled by ALUs as a bunch of separate instructions. And now on GCN, another couple of instructions have been added for the export conversion in the end. So this is basically what's happening in this shader. The first thing is that it sets up a parameter address and a primitive mask. And this is basically provided by the driver, so it comes loaded in the S2 register here from the beginning. And it's moved to a special register for that. Then the interpolation is 2 ALUs per float that you get in. Basically like an interpolation in X direction, then an interpolation in Y direction on screen. And then in the end you have the format conversion for the export, which is 1 ALU per 2 floats. And finally, it's an export instruction there with a compression flag there to indicate that we have done this conversion. So if you want to make a null shader on DX11 hardware, you might do something like this instead. We just take the SV position and return. Then it comes preloaded into registers, and you have no ALUs or anything to handle that. So there are a bunch of freebies that comes preloaded into each shader. For the vertex shader, you get the vertex index. For the pixel shader, you get the bar-centric coordinates for doing the interpolation, and you also get the screen space position. And for compute shader, you get things like thread IDs and group IDs. And this is sort of the only kind of input you get from the hardware, and everything else has to be fetched or computed manually by the shader. So it doesn't really match what APIs pretend that these things are. And one example, as I mentioned, there's no such thing as a vertex declaration. It's not a hardware thing. It's purely a software or API thing. All the vertex data is manually fetched by the hardware, by the vertex shader. So whenever you change like the vertex declaration, the driver actually has to modify your shader or at least send it to a different address. This is how it's done on GCN. The first instruction there is basically a function call, which calls a small subroutine for whatever your vertex fetch will have to be for this shader. Whereas if you look at the example on the left there, where I don't use any vertex inputs, only the vertex ID, then we don't have this function call in the beginning of the shader. So all shaders can have up to 16 scalar registers preloaded. This is the way the driver communicates with the shader. Sorry. And usually a shader resource script will take like up to 4 or 8 scalar registers. So by default, you can't really fit all that much data. So the typical shader needs to load resources from a table. So this is how it looks in the case of a texture. If you only have like a single texture sample from, then the driver can fit that within those 16 scalar registers. So then it just passes the description directly. Sorry about that. Whereas if you have like, even if you only have 2 textures, it needs to do another indirection to just pass a pointer to a list. And then from that list, it looks up the actual resource descriptions. So as I mentioned, interpolation, it costs 2 ALUs per float. And this is independent of like in what sort of slot it happens on the... So it really doesn't do anything if you try to sort of pack interpolate together, like if you have two texture coordinates, if you slap them together into a float 4, as you might have done on older hardware to optimize. This doesn't do anything on GCN. However, one thing you can do if you're passing down constant values is to use the no interpolation flag, and then it turns into a single ALU because it doesn't need to do the interpolation. It can just do sort of a mob instruction instead. The screen space position comes preloaded, as I said. It doesn't require any sort of interpolation. However, like in the past, when you had like interpolators preloaded, you could still be interpolator bound if your shader was very short. And this is still the case with things like SD position. If you have a very short shader, you can actually be limited by that. And in that case, it might actually be faster to just pass an interpolator instead. But if your shader is sufficiently long, it's going to be faster to use the SD position instead, because then you don't pay the cost for interpolation. And there's also a no perspective flag, which might be useful here. It doesn't really change how much interpolation is done. However, in some cases, it can help you take away one component, like if you passed down the W component in the past for doing perspective correction in the pixel shader, or for canceling out the perspective correction, actually. You can use the no perspective flag and save one component. So this is basically the comparison of when you have the no interpolation flag. The one on the right is just passing a texture coordinate as usual. The one on the left is passing a texture coordinate as usual. On the right, it's using the no interpolation flag, and it turns into just a mov instruction. Just pick the data from the first vertex instead. Another thing that comes preloaded is the front face flag. So it usually comes with all bits set to 0 or all bits set to 1. So the hardware doesn't really have any bool data type in that sense. All registers are 32-bit floats, or 32 bits. But in all APIs, this is declared as a bool. But you can actually, or it's documented as a Boolean attribute, but you can declare it as a uint anyway. And then you actually get these raw bits. You get all zeros or all ones. And that's actually quite useful in some cases. The typical case where you would use the front face flag for is to flip normals for backside lighting. So the example on the left here is what you probably would have done in DX9 area or previous generation consoles. This is probably how most of our code at least used to look like. And the one in the middle is sort of more DX10 level way of doing it, where you just do a conditional assignment based on that flag. And as you can see, it traces down one instruction from that. And finally, on GCN, it has this bit field insert instruction, which is very useful. It's sort of a bitwise blend based on a mask between two inputs. And since we have these raw bits of either 0 and 1, we can just feed that directly and select between two values. And then we can shave off one instruction more. So it's down to 3 instructions for flipping the normal according to face direction. So GCN instructions are quite limited compared to previous generation hardware from AMD. They have really tried to simplify the instruction set. So now the instructions are limited to 32 and 64 bits. And as you can imagine, that's not a whole lot of space to pack a lot of constant values and intermediate values into. So a lot of new constraints apply here. So each instruction can only read a single scalar register or one literal constant. The exception is if the constant falls into one of these special values here, because these are treated like they are special hardware values. And in some cases, this is very useful to have those. given this limitation. There's also similar output multipliers, which is also useful. This is unfortunately quite underused by compilers, but it is something, at least theoretically, is very useful for a lot of cases. There are some cases where the compiler actually does use this. So GCN is a scalar architecture in the sense that it's not a V-level architecture, it's not a vector architecture. From the point of view of a single shader, like from a single pixel, it looks like a scalar. Of course, under the hood, it's a bit different. So you shouldn't really confuse. It's easy to confuse the GCN's scalar and vector instructions when you hear that, oh, it's a scalar architecture, why does it have vector instructions? But if you take this, a bunch of threads together, all these scalars together become a very long simmed vector. So that's what's called a vector instruction. And the scalar is sort of a shared unit on the side that does things that are for all of these units together, for the whole compute unit. And this scalar unit, it does its execution independently. So it's sort of for free in some sense. And it does things like loading constant and control flow. For the instructions, the typical math instructions, they are full rate. They operate in a single cycle. Whereas we're talking about things like floating point add, multiply and add. Integer, add subtractions, 24-bit multiplies, and the logic instructions. The 32-bit multiply, on the other hand, that's actually a quarter rate instruction. So it's, in a lot of cases, it's actually very useful to use the 24-bit and get a lot of speed from that. Type conversion is full rate on GCN. It used to be slower. It used to sit on the transcendental unit on older AMD hardware, but nowadays it's full rate. Operations like floor, ceiling, round, etc., they're also full rate. At half rate, we have double adds. That's basically the only instruction class that's half rate as far as I know. Quarter rate, we have transcendentals like square roots and reciprocals and so on. When you work in doubles, multiplies and fused multiply and adds, these are also quarter rate. And as I said, integer 32-bit multiplies are quarter rate. And it's sort of for free the scalar operations, at least in a normal case where you're sort of dominant, when the shader is dominated by regular floating point math. These sort of become for free because they handle on the side independently. Of course, it's possible to make a shader that's dominated by scalar operations, and in that case, it's not for free anymore. The things that are super expensive include things like doing integer divides. It's slightly less horrible if you have on side, but this is not natively supported by the hardware, so it's emulated with a lot of instructions. And as I mentioned before, that's also the case for inverse trigonometry. One thing to note with GCN instructions is that you can't really look at the instructions anymore and sort of have an idea of the performance, or you can't just count them. You have to look at the individual instructions because they have different latency. Whereas in the past, if you look on previous generations hardware, you can just count the number of VLIV slots, and that gave you a good idea what the final performance would be, at least if it was ALU bound. But that's not the case anymore. You have to look at individual instructions. So something I focused quite a lot on in my talk last year was on the multiplies and adds. Because of these new restrictions on GCN, in many cases, actually, still it turns into two vector instructions, like in all these three different classes of all these ways of doing it. Well, the first one is actually an add followed by multiply to illustrate. And the one in the middle, if you sort of convert that to a multiply and add form, You still have 2 vector instructions there, and even added a couple of scalar instructions. And if you fetch things from a vertex buffer, even here it had to add its move instruction first before doing the multiply and add. So you might think that maybe it's obsolete now to write in multiply and add forms. Well, it's certainly not the case. In most cases, it's still beneficial. But there are these special cases where it doesn't help. And this is usual to keep in mind. However, it's still usually beneficial. Like when you have none of these instruction limitations applying, of course, it's still going to be a multiply and add, going to be faster. Or whenever you use any of these inline constants, it's also going to map into a multiply and add. And even if the input is a vector, you're still going to see a benefit of writing multiply and add form. So here's a comparison: add multiply on the left and multiply and add on the right. So the first row here is basically comparing when you have a single immediate constant. In that case, it can fit within the instruction limit. For the hardware, it turns into multiply and add, as expected. And the second case is where you use an inline constant, one of those special values that I talked about earlier, 0.5 in this case. And then it also maps into a single multiply and add instruction. And this is the vector operation case. So it's not, it doesn't turn from 8 instructions here for this float 4 into 4 instructions as you did in the past. It turns into 5 instructions, but 5 is still less than 8, so still quite a bit of benefit. It just added a single move instruction there instead of expanding to 4 instructions. One thing you might have done a lot in the past is sort of vectorize code in order to hope that it would match better for the hardware. If you had vectorized hardware like in previous generation consoles. Usually this doesn't really do anything at all on modern hardware. But there are actually a few examples of cases where it can actually hurt you to do that. And this is one example I found. If you do something like this to in the past, you might want to use the dot product to sort of take advantage of the vector instruction on that hardware. But if you write it like that nowadays, it actually, because of the semantics of the language, will do the dot product first and then do the subtraction in the end. So you can't do that as like a multiply followed by multiply and add followed by multiply and add. Instead, it has to do the mul first, multiply and add, and then subtraction in the end. And this adds one instruction in this particular case. So in general, doing this sort of vectorization these days is really not something you should be doing anymore. One of the things on the hardware that hasn't really kept up with the evolution of other parts is the raster operations. They don't scale up a lot between different generations. Usually, you can keep the same number of ROPs many generations. And one impact of that is it's actually quite hard to utilize all your bandwidth if you're going through the ROPs. If you're like filling a buffer or something with some initial conditional values, if you do that with a pixel shader and it goes through the ROPs, you can't use all the bandwidth that's available on the chip, simply because you're limited by the ROPs. Even if you fully utilize the ROPs perfectly, you're still not going to use all the bandwidth that the chip has. And that's true for all hardware. It's true for PC hardware. It's true for the new generation consoles, at least for the smaller formats. If you have a wide format, you might be able to become bandwidth bound instead. But if you have smaller formats, it's very easy to be ROP bound. So what you can do in this case is simply bypass the ROP and use a computer shader instead. So anytime we have anything from like 64-bit formats or anything or less, it's usually beneficial to use a compute shader to just fill the buffer instead of going through a pixel shader. Because then you have just raw writes to memory instead of going through through this ROP state with all these restrictions and so on. If you do this right, it's easy to be bandwidth bound instead. And we have done a couple of cases where we've seen like 60 to 70% bandwidth utilization improvement. So it can make quite a big impact. As I mentioned before, branching is managed by the scalar unit. So basically how it works on the hood is that execution is controlled by 64-bit masks. That's basically just lies in a scalar register. And the shader can actually just modify these bits as it wants. And when you do a branch instruction, you just look at the mask and does the branching from there. So the branching doesn't actually count towards your vector instructions. So in that sense, the branching is for free. Although there are, of course, always limitations with or implications of using very branched code. The main problem is usually that it increases the number of registers, which can impact your performance in other ways. So if you have that case, in some cases where we're just picking between two different values, you can do a conditional mask. Usually the compiler does this automatically if you use the question mark operator there. Semantically, though, it's a branch to have that operator there. Usually the compiler optimizes it, but there are some compilers that doesn't do it all the times. So in that case, it can be good to use an explicit conditional mask for handling that. Integer multiplies, the 24-bit multiply is full rate, as I said before. The way this works is that even though the input registers are obviously 32-bit, it only uses the lower 22-bit. However, the result that comes out in the end is the full 32-bit. And you can actually even get the upper 16-bit with another instruction. So you get sort of the full 48-bit result. So this is a 4 times speed advantage over 32-bit multiplies. Another advantage of the 24-bit multiplier is that there's also a multiply and add instruction for that. So you can also get this addition for free. This is not the case for 32-bit multiplies. It doesn't have. There's no 32-bit multiply and add instruction. And if you had this 24-bit multiply and add, the addition part of that is actually full 32-bit. It's only the multiplication that is 24-bit. So if you look at these examples here, if you do a 32-bit multiply like on the left hand side there, it's going to take 4 cycles to do that multiplier. Whereas the 24-bit one takes a single cycle. And if you add that addition in the end, with 32 bits, it's going to turn into 5 cycles, another cycle for that addition, whereas this baked into the instructions is still only a single instruction if using the 24-bit instruction instead. As I said before, integer division is not natively supported by the hardware. Obviously, the compiler does some optimizations here if you have a constant. Like if it's power of 2, it does the obvious thing and turns it into bit shift. It also does some less obvious optimizations, like if you divide by 3, there are some known algorithms for generating magic shift and multiply constants to turn it into a faster operation. And the compiler uses that. So if you divide in by a constant, it's usually quite okay. It's not that many instructions. It can be anything from I've seen 3 or 5 instructions for handling that. However, in the general case where you're just dividing by any random integer, it's going to be a lot of instructions. We're talking about 40 cycles for unsigned and about 48 cycles for signed. So that's very expensive. So it's something you should try to avoid if you can. And you should always stick to unsigned if possible, because it's usually faster. Even in this, if you have this divide by constant value, it actually helps to reduce the number of instructions the compiler have to emit to handle the sign. And if you know that your input is restricted in some way, the range is low, you can actually implement your own 24-bit version of this to get a bit of a speed advantage there. For instance, if in the case you're dividing by 3 here, you can just do this mul24 with this magic constant and shift 17. And this works as long as the value is somewhere between 0 and up to 90,000 something. And it can be a pretty good speed advantage to do that. And finally, if you have a special case where it works, you can actually convert your integers to float and do the division there and convert back. This obviously has a bunch of problems with the rounding and so on that you might have to take care of. And it probably doesn't work. It doesn't work in the general case, but if you have a case where it does work, this is going to be a lot faster. You can do that sort of thing in about 8 cycles. Doubles. The first thing, of course, when you think about using doubles is, of course, do I actually need doubles? And in my entire career, doubles have been the answer in pretty much only in Mandelbrot and a bunch of hacks. But of course, I know there are people working on scientific stuff, and if doubles is really required for your algorithm, then of course you should take advantage of it. So in that case, there are a few advice here as well. Obviously, the same thing is applied with floating point. You should use the fused multiply and add if you can. One thing to note here is that there's no double equivalent to the float multiply and add. There's only the fused multiply and add. And the difference between these two is that the multiply and add does the rounding in between the multiply and the add operation, whereas the fused multiply and add only does the rounding in the end. So a fused multiply and add is usually preferable because it's more precise, although it's not compatible with the IEEE standard in the same sense. So usually the compiler outputs a multiply and add instruction for float when it can, simply because it's more safe in a sense. There's no direct support for division of for doubles, actually not for floats either. It's all handled by the reciprocal and the multiply. And for floats, the compiler is happy with just those two things, because the standard allows up to 1 ULP there. It's possible to get the 0.5 ULP precision if you absolutely need that. The hardware has a few instructions for handling that for improving the rounding. But it's a lot more expensive. And the same is true for doubles, even more so for doubles. And by default, the compiler actually does a division as the full 0.5 ULP, so it's really, really expensive. So if you don't really care about that, you can actually do an explicit RCP instead. And then it gets a lot cheaper, even though it's still not cheap, but it's a lot cheaper than doing it as a division. One thing that's going to be more and more important these days is to pack your data, because bandwidth doesn't scale as fast as ALU is doing. So it makes more and more sense to pack your data as compact as possible. And the hardware has a bunch of new interesting functions for that. You can convert between 32 and 16-bit floats, for instance, in a single cycle. And it also has bit field manipulation instructions. So if you're packing, say, a 16-bit color in the good old 565 bit field, you can actually just extract those in a single cycle for each component. So it's actually quite fast. Something I mentioned in my talk last year was that you should prefer conditional assignment or sign. This is something I'm repeating now again because it's a very important thing. Because the default implementation of sign is very poorly implemented. It's very slow. If you do conditional assignment, it's a lot faster. If you just check if x is greater than 0, then 1, otherwise minus 1. It's a lot faster. And similar with the step function, just do a comparison and then output the results. The way these functions are typically used is that they're probably multiplied by some value in the end. And these things, if you do it as a conditional assignment, you can just merge that into the two values that you're selecting between, and you get that sort of thing for free. Whereas if you actually use the sign and step function, so in addition to this being slower, you also get the additional cost of actually doing that multiplying there. The hardware has a bunch of new interesting features as well. It has instructions for doing the minimum of 3 or maximum of 3 and the median of 3 values. This can be quite useful if you do some things like post-processing and want to do a bigger reduction of data. One interesting trick here is actually the median of 3 can also be used as a general clamp for values. If you just pass your x values and then your mean and max, the median actually returns a clamped value between your mean and max, if you think about it. It's not obvious until someone points it out to me. At least it wasn't obvious to me. And that's actually a very useful thing. Textures. As I mentioned before, all these descriptors for textures and samplers, they are data now. They don't reside in any hardware registers. They reside in memory. So they are explicitly fetched by the shader. And this means, of course, that the less data you need to fetch, the better. So if you can use the load instruction instead of using sample with the point filtering, that's going to be a lot better. Because then you don't need to fetch a sample state. And whenever you have a sample state, you should try to reduce them as much as possible. And don't just, like if you're coming from a DX9 engine, you probably have this sort of artificial link between sampler states and textures, where texture 0 samples from sample state 0 and texture 1 samples from sampler state 1 and so on. But in most cases, all these are going to be the same. You're probably going to use the same sample state for a normal map for the diffusion, for your properties map and so on. And in that case, you should only pass a single sample state and use for all the 3. And that's going to reduce the number of sample states that the shader needs to fetch. QMaps, as I mentioned before, it adds a whole bunch of ALU instructions for doing that normalization of the texture coordinates. Usually this is not something you can really avoid, but in some special cases, like if you're having your skybox as a cube map, it might actually be faster to just draw that as 6 2D textures instead, because then you don't pay this cost for doing this coordinate normalization. If you've used sample offsets on texture instructions, in the past you might have used this on the load instruction. This is not optimal for the GCN architecture because it's not baked into the instruction anymore. Previous generations had it baked into the instruction, but now it's not. So it's actually doing that offset by doing a bunch of ALU work. So it's actually adding that offset, doing a sample, adding another offset, doing a sample, and so on. In many of these cases, you might consider using gather instead to grab this data. It's probably going to be faster if you're only sampling. You're probably sampling the neighboring data if you're using texture offsets. So gather usually is the way to go here. For the general sample, on the other hand, the offsets are still baked into the instruction, so they're perfectly fine to use there. The registers is the number of registers in your shader. This is something that's been becoming a bigger problem for GCN than it has been in previous generations. It can really limit your performance. So you should always try to keep your registers down as much as possible to improve the latency hiding for all memory operations. Generally speaking, fewer registers is better. Unfortunately, this is kind of a hard problem it's very hard to control for a shader writer it's not easy to sort of just change a line of code and suddenly it's a fewer operations, a fewer registers. But a few things that you can do that sort of helps the compiler to to allocate fewer registers. One thing is that if you're like having a loop over a bunch of items and you do first one kind of work and then do another kind of work, it might actually be better sometimes to actually loop twice, because then the shader becomes more, say, long thin instead of wide with a lot of things, a lot of data that it needs to hold at any given point. And one thing that people are sometimes doing is like they sample the texture, then they do a bunch of things, and then in the end just output alpha in the end because you had an alpha from the texture sampling. So just return it even if you don't really aren't actually using that alpha value. And this is, it's much better to just return 0 or not just use that. Otherwise, that alpha value from the texture sampling and all the way down through the shader will actually occupy one of those registers. And that's quite a bit of a waste. Another thing you might consider is to use a specialized shader. Like if you have a big Uber shader, you're paying the cost, for the worst case in terms of registers. So if you can sort of make at least a few specialized shader and kind of cut away features that you aren't using, that will give you a faster shader and fewer registers. And also look at things like branch nesting. Even if branches are fast in the hardware, the impact on the registers is usually the thing you should look out for. So if you can sort of reduce the nesting of branches, that usually has a good impact on the number of registers. And finally, to the rant part of this talk, a few things that I keep seeing that I just wish people that write shades should stop doing. I often see people raising color to 2.2, obviously compensating for some sRGB thing, except that's not sRGB at all. It's a close enough approximation probably for a programmer, but trust me, I talked to artists. We have cases where we switch to actual sRGB and they notice the difference. So it's really, and it's almost always certainly a sign that you did something wrong, because the hardware has these conversions anyway. You should just use the built-in hardware. And the same with textures. There are signed texture formats for. Not every format has a signed version, but if you're using a texture format that has a signed version of it, you should absolutely use that instead of like rescaling in the shader. Even if it's not a lot of ALU instructions, but still it's better to have 0 than 3 for a normal layer. As for on the compiler side, there are some things that compilers are doing that I think they shouldn't be doing. The FXC compiler, for instance, takes, if you multiply by 2, it turns it into an addition. And that might make sense for integers maybe, but for floats, and I really don't see the point of that. And it confuses the optimizers. It's harder for the optimizers to actually use this output multiplier that it has on and these special values that it has. Another thing the FXC compiler is doing is turning, in some cases, a saturate into a min, and it just adds one instruction. And that's because it's not treating saturate as a first-class citizen. It just treats it as a min and max, and then it optimizes away the max, and then suddenly you have only the min in the end, and that actually slows down your code. And similar, if you have something like x times 4 plus x, the compiler realizes this is the same as x times 5, so it does this conversion for you. It makes sense for floats, but it doesn't make sense for integers, because 32-bit integers, they are 4 cycles, whereas a bit shift is 1 cycle. So in this case, you could actually, it would be faster if it just passed it on as it was, and the compiler could just turn it into a bit shift and an add instead of a 4-cycle multiply. And even if you write it explicitly like a bit shift and an add, the compiler still realizes this can be turned into a multiply by 5, and that's really annoying. It's hard to even, you can't really work around the compiler in this case. if you're doing a lot of times when I do prototyping, I find myself doing like magic float values. And when I do some things like that, as float with some value, and it's sufficiently small, such that it actually becomes a d-norm, the compiler just turns it to 0 for absolutely no reason. And in my opinion, this is a bug, even because it really should just be a bitwise copy, in a sense. A lot of compilers spend a lot of time doing, I don't know, probably trying to unroll loops, even if you take them as a loop. If you have a shader with like looping from 0 to 10, and then you turn that to loop 0 to 100,000, suddenly your shader takes a lot longer time to compile, even if you take it as loop, which makes no sense at all. In some cases, when you multiply things by a vector, it does things a little bit different. Like if you have a 0 in the middle of the vector, you might think that the compiler would optimize that away, but if it's within a vector, it actually turns that into multiply by 0 and outputs that kind of instruction, which is probably not what you want. So, things that the compiler should be doing. If you find an x multiplied by 5, you should, of course, do it the other way around, turn it into a shift and an addition, because that's just 2 cycles instead of 4. And of course, if you can detect cases where the input is within a certain range, such that you can use multiplying the 24-bit multiply, you should of course use that. I've seen some cases, especially on older hardware, that this happens, but where it doesn't happen on GCN for some unknown reason. So this is something that would be good if the compiler actually did. Obviously, I want a lot more intrinsics for any of these new instructions that's available on the hardware. I would really like to see that exposed to us as programmers. A lot of things are happening on that side, on the console side, but I would like to see more on the D3D side as well, in the D3D bytecode. It's kind of limited in many ways. It doesn't have operations matching those, what's on the hardware. And the final point here is that's more like an HLSL language thing that keep annoying me, that type conversions it accepts any type to anything. If you have, for instance, you do a load on a texture, which takes ints as input, you can pass floats, it just automatically converts it, no warnings, no nothing, and it's just going to be a lot slower. And you might not even know about it. So I would like to have that, I would preferably have that as an error. You have to do like explicit costs. That's my preferred model. There are a lot of things left on the hardware that hasn't really been explored. So this is just random ideas here, or random things that might be possible to explore. I don't know for what yet, but it's at least interesting. Because it has this sort of general swizzles, you can just swizzle data between different lanes, different threads that run on the same compute unit. You can probably use that for something, just communicate and pass along data in some way. I don't know how you'd use it, but it's probably useful for something. And similar with branching, because all of this data lies in a scalar register that you can just read, this could also probably be used for. One thing I think it would be useful for is just as a debug visualization to see where are your branches coherent and where are they not. Just look at that register and see if they are all zeros or all ones. The hardware can do virtual functions. I'm not sure if it's something you want to use. It's probably useful for someone. Things like goto is something the hardware can do. Just go to from any branch from anywhere in the shade to anywhere else. Again, I don't know if there's a really use case for that, but it's probably useful for someone. Finally, these references for this stuff, especially the third link there, there's very useful information for all the GPU, what's happening in the GPU. All of this is very well documented by AMD. You can just go and read it. And a lot of this talk has been derived from just reading this documentation and then just look at shaders and see if I can tweak my shader to turn it into whatever I see is available on the hardware. So that is something I recommend everyone to read. And with that, I'm ready to take questions. Go to the mic, please.
Yeah, on that second to last slide, the first two things, I cannot agree with you more. But as far as cross-lane communication, in almost every GPU code or compute, sooner or later you have to do that. And the second, the one after that, being able to access the predicates, of a vector test, that encoder, that is actually a primitive. It's like called any and all. It's very useful. And then you actually you also can do pop count on it, which you can count how many passes the test and how many don't pass the test. Those are very useful operations. So yes, use your power to try to get whoever the compiler people to give it to us. But I have a question about the sign optimization. So what I've been doing is that I've been using the float and I'm taking the sign bit and I start doing logical operation like XOR and 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 things. Is that? But I never scrutinized the code to see what it generates. But is that kind of bad?
I've been trying to do that sort of thing, but it's actually very hard to beat just doing a comparison and a conditional assignment. That's two operations. I've been thinking about ways to sort of squeeze it into one by using any sort of magical instruction that happened to be available, but I didn't really find any.
So but if you have the composite sequence of tests, like a Boolean expression that has like some ifs and I guess so you just do natively as floating point comparison?
Yeah.
Okay. All right.
So I was looking, oh God, my voice does not sound good today. I was looking into something innocuous in shader code a while ago, and I set out to figure out kind of for whatever this instruction is outputting, how many GPU cycles or equivalent or whatever it's actually happening. And in trying to figure that out, what I kind of discovered from a friend of mine who's working on DirectX is that what the shader compiler does, it's spitting out basically that code becomes like an intermediary language that then gets recompiled by the driver for whatever driver you happen to have, for whatever card you happen to have. So in terms of looking at my shader instructions that are actually being output, how closely can I map that to what the device driver, when it compiles that, is doing to mangling my code? I mean, could that potentially unmangle some of the things that you were saying why our compiler is doing this? I feel like there's an impedance mismatch there, so is there?
Yeah, I mean, it's definitely a problem that you have an intermediate. I mean, it's good in other ways to have an intermediate language, of course, but it's definitely a problem also for optimizations that you have. That has to go through from a HLS through an intermediate language and then to a hardware language, and then you lose information in the middle there. So, I mean, in a lot of cases, like simple optimizations, things like multiply and add and so on, this definitely go through all the way. You can look at the final shader and you see that it's very deterministic, actually. But for things where you have like special hardware instructions that you might want to use, if it's not implemented by the D3 bytecode, it's very hard to write the shader actually to take advantage of that. Sometimes you just sit there and squeeze in many ways, try to make it give some sort of hint. Maybe if I write this way, maybe the optimizer in the end realizes that this actually perfectly matches to this instruction that it has. But in a lot of cases, you kind of give up if it's too big this mismatch between the hardware and the D3D assembly.
Okay. And one other thing really quick. So I remember a while ago somebody said there's a bunch of overhead switching from to and from compute shaders, and so only do it once and then try and get everything done. And then is that still the case? Is there overhead that I should care about if I'm using compute shaders for some things? As you mentioned, using that to become bandwidth bound instead of I forget what the slide said. So for that, should I try to avoid doing that, or does it not matter?
Okay, repeat that. I didn't get what.
Yeah, if I'm using compute shaders for some things in my graphics pipeline, and I'm switching back and forth from compute shaders to pixel shaders, for example, is there any overhead to just kind of randomly using compute shaders? I recall in the past that was a bad thing to do. Is that still the case, or am I just totally crazy?
You mean like in terms of driver overhead and so on?
Right, in terms of any overhead, I have no idea. That's why I'm curious.
I'm not sure, actually. I don't know how big the impact is on that. We aren't really switching between compute shades and picture shades a lot. We're just doing a few things here and a few things there, and then that's sort of it. So honestly, I don't know. And I think we're actually out of time now, but if any of you have more questions, just come up to me here in the end. Thank you, everyone.